In the previous lecture, we discussed about the sequential circuit, and especially we talked about different flip-flop circuits. And based on their operations, we come up with the different kind of flip-flops. Initially, we discussed RS flip-flop, and then the extension of RS flip-flop was the D flip-flop, and that can remove the problem of like the race around problem just by keeping both the inputs in complementary form. Okay, and then we talked about, suppose if I have to make a toggle kind of thing, because in RS flip-flop we had a race around problem or indeterminate kind of states. So to avoid that one, we can have one more variant, especially with the two input flip-flop, and that was the JK flip-flop. And the problem with the RS flip-flop was suppose something like the race around kind of problem, and that was removed with the help of JK flip-flop, where the output was fixed, that was toggled for each clock pulse. Okay, so this was one of the solution to avoid the race around problem. And then we talk about, because if I have to design some counter and the toggling kind of phenomena is required, so for that purpose, just we need to connect both the inputs to the same signal, and then we call it the toggle flip-flop. So this is this kind of the circuits which we have already discussed are the sequential circuits. Now let us talk about, so these all are the well-defined circuits, like the operations are fixed, we have the input, we have output, and accordingly we are managing the things. But what happens if I have to design a sequential circuit based on our requirement, based on the logic structure, or based on the state diagrams? Okay, so the sequential circuit can be designed with a two way. The first way could be like, suppose I have a circuit, like the flip-flops are connected here and there are some logic circuits are there, and then accordingly I have to analyze those circuits. So this is one of the way for analysis. And the second way could be like, suppose I have a state diagram is given where the input and output relations are given, and based on that I have to design the circuit. Okay, so like both the way is possible. So in this particular lecture we are going to discuss how we can design the sequential circuits based on our requirement. Basically, if we talk about the sequential circuits are of two types. One is the asymmetrical asynchronous one, and the next one is the synchronous one. Like, so basically the sequential circuit, or simply asynchronous kind of the sequential circuits, means if we are giving input, changing the input at any time of any point of time is possible in this kind of logic. Let me repeat it again what I'm saying. Suppose if I'm talking about the asynchronous kind of sequential circuit, so the change in the input at any time is referred under this category. Okay, but if you talk about the symmetrical one or the synchronous one, in that case the inputs will be reflected at the output when clock will be reflected. Okay, so let me summarize it what I'm saying. Suppose I'm talking about a sequential circuit. Okay, in sequential circuit we can classify with the two way. The first way is like, suppose if there is some change in the input in the sequential logic, and immediately I am getting reflected, output is getting reflected based on the input. So we can call them the asynchronous one, because it does not depend on the clock. But there could be one more arrangement in the sequential one, where we will have a clock pulse and we will have an input, and if there is some change in the input and the clock is not activated, so the output will not be changed. But if clock is activated and if there is some change in the input, then output will be reflected. What it means, the output of these kind of sequential circuits are depends on the clock, means they are synchronous, they are synchronized with the clock. So we can call them the synchronous sequential circuits. So this is the category that we can decide, okay, based on their operations. So based on these all things, we can classify the sequential logic or the model of the sequential circuits in the two way. The first model could be the Murray model, and the second one could be the Mealy model. So, okay, so any of the sequential logic, either it is flip-flop or any register, counter, so all this comes under either the Murray model or the Mealy model. Okay, I will differentiate about both the models, and I will let you know what is the difference between these two models and how we decide which kind of model a particular circuit is. Suppose I have designed one flip-flop, so whether that flip-flop will be considered under the Murray model or it will be considered as a Mealy model, that depends how the circuit is getting arranged, what is the arrangement in the circuit. Okay, so what is the arrangement, what is the difference between these two things, we are going to discuss here. Okay, so let us start with the first thing, like Murray model. Okay, so what is the Murray model? Before we discuss about the Murray sequential model, we need to understand few things. Suppose I have an input signal of a sequential circuit, and suppose I have a combinational logic circuit which I am going to operate. Okay, before I discuss here, let me recall the sequential logic. The difference between the sequential and the combinational logic is, like, if there is some memory kind of element or storage element after this combinational logic circuit, then we can consider them as a sequential one. So sequential means if they have some storage capability, if they can hold, they can latch some data, so we can call them the sequential logic. Okay, so in summary, we can say the sequential logic circuit has some memory kind of section or memory kind of devices that can store the present state, and that can be utilized when we are operating in the next state. Okay, let me repeat it again what I'm saying. In the sequential circuit, we have a memory kind of arrangement. Memory means it's not like there is a storage. There is an arrangement like feedback path in such a way that they can hold the data and they will operate the current output in the next stage. Okay, so we are calling it the memory one. So for that purpose, we can use the state register. State register is nothing but this is one kind of the set of flip-flops, and this is nothing but this is the memory. We can simply call them the memory section. Okay, that can store some of the states. Okay, so here we have a combinational logic. Here we have a register or the memory element, and we are getting some output out of this. And if I used to feedback this output with the combinational logic circuit, then this circuit will become the sequential logic circuit. So we know these things. Okay, so what kind of arrangement we have here, this we can refer is the sequential logic circuit. Now let us come to know what this Murray model is, how we can differentiate the Murray model and the Mealy model of the sequential circuits. Okay, so as of now, what kind of structure we have here, this is nothing but this is same like a sequential circuit, like what we have discussed before. Okay, now if I want to differentiate between the Murray and the Mealy model, I must have one combinational logic circuit. Again, one more combinational logic circuit is required, and then how this combinational logic circuit is connected with the sequential logic and with the input, that decide whether I am considering it as a Murray or the Mealy model. Let me repeat again what I'm saying. Whatever the block we can see here, this block is nothing but this is the sequential logic circuit. Okay, this is what we have already studied. But to differentiate the Murray and the Mealy model, we need one output combinational logic, and that decides whether that model is the Mealy or the Murray. Okay, so means we need one additional combinational logic circuit to differentiate these things. Now once we are ready with this output combinational logic circuit, then because that output of sequential logic circuit is connected to the input of this output combinational logic circuit, but we have some other things as well, because for this output combinational logic circuit, the output of sequential logic will be treated as one of the input. Okay, so this is nothing but this is one of the input for this output combinational logic circuit, and we have one more input for the sequential which we have already considered. Okay, so we can have a two kind of input. One will be this one and the second one will be this one. Okay, so if the output combination logic circuit is not depends on the current input, like whatever the input I have here. Let me repeat again. If the output combination logic circuit, whatever I have considered, is not depends on the input of the sequential logic circuit, whatever we have decided over here, then we can call them, these are the Murray machine or the Murray model. Okay, so the Murray model is the simple difference between the Murray model is like, so whatever the sequential circuit we have, and if the output of the sequential circuit is connected to the output combination logic circuit, and if the output combination logic circuit is not depends on the input of the actual circuit, then we can call them, this model is the Murray model or the Murray machine model. Okay, and if you talk about the second kind of arrangement, suppose I have an input, I have a next state combination logic, and we have an output, and if I have feedback it, so it's sequential logic circuit. Okay, now if I have to make it the Murray or the Murray model, then I need one output combination logic circuit. So up to this, we got the same kind of structure, whatever we have seen in the Murray one. But the actual difference between the Murray and the Murray model is, if the actual input, whatever we had for the sequential logic circuit, is also used to control the output combination logic circuit, then this kind of model, we call it the Murray machine model. Okay, so the actual difference between the Murray and the Murray model is the simply the feedback. Like if the output combination logic circuit is the function of the output of the sequential logic as well as the actual input, then we can call them the Murray model. And if the output combination logic input is the function of only the output of the sequential logic circuit, then we can call them the only Murray model. Okay, so this is the only difference between these two things. Okay, hope the points are clear. If you have any doubt at this point, you can ask the questions.
Sir?
Yes.
What is this state register?
State register is, I just told you, let me explain it again. Suppose I have to make a sequential logic circuit. So if you can recall here, if I have a combination logic circuit, okay, so this is the combination logic circuit, and I need to feedback with the input to make it as a sequential logic circuit. I already told you before. Okay, so suppose I have a combination logic circuit, and if the output of this combination logic circuit is feedback to the input of this combination logic circuit, so we can consider it as a sequential logic circuit. So this is one of, so here we have a unity gain feedback. Okay, now the second kind of arrangement could be, suppose I have a combination logic circuit, and if I am getting some output, and the output is connected with the input with some feedback path, then this is the second kind of arrangement of the sequential logic circuit. Now what it means, if we have done this kind of arrangement, now let's simply let me draw a simple structure. Suppose I have an inverter, okay, and I have another inverter, and output of this one is connected to this one, and output of this one is connected to this one. So here, whatever the logic I will give here, 0, so it will be 1, and 1 input of the second inverter will give you 0. So they will latch the logic. And if they are able to latch the logic, so what it means, they are able to hold some of the state at some node. And if they are able to hold some state, so it means they can store the logic. And I just told you, the flip-flop is the basic element which can store a single bit. Okay, so if they can store a single bit, what it means, and the register is nothing but the group of flip-flop is known as the register. Okay, so state register means that can store a state information. What is the state of current output, and to store that one, we need a state register. Okay, so state register is nothing but that indicates the memory kind of property that can be utilized to execute the next state. Suppose I have given some input, I am getting some output. Okay, in the next state, the same output can be considered as an input for the next state. Okay, and what it means, because we are considering the current output that can be considered as the input for the next state, what it means, we have held that information for some period of time. Okay, and if we are holding it it means there is some memory property, and if there is some memory property, what it means, it can have register. So register is nothing but if we have more than one bit information that I have to store, we can call them the register. Okay, so here for now you need to simply consider like the state register means that can hold the current status, current state of current output. Okay, that can be utilized for the next state. You got the point?
Yes, sir.
Okay, so basically state register is nothing but this is a storage element which can store the logic. That's it. Okay, so that it can be utilized in the next state. Okay, fine. So this is the so the basic difference between the Murray and the Mealy model was the feedback or the connection between the input and the output combination logic circuit. Okay, so based on that we can decide whether it is we have to apply the Murray model or the Mealy model. One more thing before we study about the Mealy and the Murray model, because see, we are about to understand two different models for the sequential circuit. So we need to know about the different parameters about the sequential circuit models. Okay, so what are those terminologies or some notations about the Mealy and the Murray model? Let us try to check it out. Okay, first information that we should know about any of the sequential circuit model is the input variable. What is the input variable? Yeah, whatever the notations I will explain here that are used in the next few lectures. Okay, so you should know all these things. What is the meaning of these things? So the first parameter, first notation that we have to discuss is the input variable. What is the input variable? All the variables that are required for the sequential circuit that will be fed in the circuit are known as the input variable. Okay, so all the inputs which we are providing to the sequential circuit will be the input variable. Output variables are all the variables that are produced by the sequential circuit are known as output variables. So these are simple things. Important thing that we have to consider is the state variable. State variables means like I just told you, Mealy and the Murray model has some sequential circuit, and then we have a combinational logic circuit. So here I have some input. Okay, here I have some output of the Mealy-Murray model. This is the output of the sequential. Let us assume it is a sequential. Okay, so if this is the sequential circuit, then the output of sequential is this one. This is the output of sequential logic. Okay, and this output of the sequential logic will be treated as an input of the output combinational logic, and this is the output which we are getting the output for the overall sequential logic circuit. Let me repeat it again. Here we have an input, we have a sequential logic circuit. Output of sequential logic circuit is connected to the output combination logic circuit, and the output combination logic circuit will give you some output. So these are the input variable. These are the output variable which we are getting. The state variables means output of the memory, whatever the sequential logic circuit we have considered, these outputs, whatever I will get, these are the state variables. So the output of memory, whatever we have used, let me go back to the previous slide. So if you see here, this particular point is the output of the memory. Okay, so we can call this variable as a state variable. Okay, so the output of this one is the state variable. So the first terminology is the input variable. So these are the input variable. Second terminology is the output variable. So these are the output variable. Third terminology is the state variable, means the output of memory is known as the state variable. Here, these are the output. There may be some possibility that the output combination logic circuit can have some additional input than this one. Okay, whatever the output of state register we are getting, that will be connected to the output combination logic. That is perfectly fine. But we can provide some input as well. Okay, additional input as well. So these inputs are known as, so let me go back to the next terminology. So the excitation variable. So excitation variables are the input to the memory, whatever the memory element we have. So whatever the input we are providing to the memory elements, those all are the excitation variables. So let me go back to the slide here. So these are some of the input. Okay, so these terminology of these terms are known as the excitation variables. Okay, so state variable are the output of this one, and excitation variable are the output of or the input of the memory or the flip-flop which we have provided over here. Next terminology is the that we should consider is the state. What is this state? The state of a sequential machine is defined by the content of memory. What kind of content the memory has stored, that we call it the state. Okay, and the relation between the state variable and the possible number of states are given with the help of this relation. 2 to the power x is equal to y. What does it mean? Here x is nothing but the number of state variables like flip-flops. How many flip-flops we have in that circuit? Okay, so here x indicates the number of flip-flops and y indicates the maximum number of states are possible. Okay, so the total number of states in any of the sequential circuit that decide how many sequential circuits or how many flip-flops we have. Okay, so this is the relation between the number of flip-flops and the maximum number of states possible. Okay, so the state is nothing but the content of the memory. Whatever the content of the memory is, like, see, suppose I have a one flip-flop. So in one flip-flop I can have a two kind of content. Either it can store 0 or it can store 1 if I'm considering only q. Okay, if I have a two flip-flops, what it means, one flip-flop can store 0, second one can store 0, one can store 0, second one can store 1, and vice versa. The total we have a 4 possible combinations. So the total possible states will be 4. So the number of states, that depends how many state variables we have, okay, or how many flip-flops we have. So this is the relation between the flip-flops and the possible states. Okay, so this is the important thing. Next and very important thing that we have to consider is the state table. What is this state table? State table is nothing but the behavior of sequential circuit is determined from the input, output, and its state of the flip-flop. Let me repeat it again. Whatever the sequential circuit we are designing, the behavior of all those sequential circuits are determined by the input of that circuit, output of that circuit, and state of the flip-flops. Okay, whatever the flip-flops I have, whatever the state they have stored, means the present state that need to be considered in the next state. So this is the status of any of the flip-flops. Okay, so the state table is nothing but the information related to the input, output, and the function. So these all are present in the state table. Whatever the status of input, whatever the status of output, and what is the status of state tables or state information, that are given in the state table. So state table is nothing but a tabular method where we can explain the input patterns, outputs, and the state information. So this we call it the state table. Okay, next and very important parameter is state diagram. What is the state diagram? State diagram is nothing but generally states are represented by their binary equivalent values. Whatever the state, either we can have a state 0 or we can have a state 1. If we can recall state table for any of the flip-flop, so we can have a QT can have a two states, either 0 or 1, and based on that we saw like what will be the next output, what will be the next input, something like that we saw in the previous lectures. Okay, this kind of structure we saw in the previous lectures. So generally we represent in either in 0 or in 1. Okay, so the generally states are represented by their binary equivalent. So the information available in the state table is represented graphically in the state diagram. So state diagram is nothing but whatever the information is available in the state table, those all are represented in terms of graphical. So this representation we can call them the state diagram. We have already seen for the flip-flop. Okay, so this is what the state diagram is. Now, because we know that we can have a two kind of model for any of the sequences circuit. One could be the Mealy model and the second one could be the Murray model. Okay, if we know, we can have a two different kind of models. So how we can represent the state diagram for these two different kind of models? So let us try to understand these two things. Okay, suppose I have, let us assume x is the input variable, y is the output variable. Okay, so these two are the input and output variables. Okay, now what we are considering, a and b are the two different states. Okay, I just told you what is the state. State is the content of the memory. What is the flip flop I have used? What is the content stored in that? That we call it the state. And let us consider the flip flop or the memory element has two state. Let us assume these are a and b. Okay, so let me repeat again what I have done. Let us consider x is the input variable, y is the output variable, a and b are the two states. Okay, if we know all these thing information, then what will be the output? Okay, so let us consider we have given some condition. If currently I have a state a, so that will change to the state b if input is x is equal to 1. Means if the x is equal to normal, if the input is x, and that will produce output y. So this is one of the condition. Second condition, yeah, this condition can be anything. It's not necessary that condition will always be same. I have just given two conditions to understand or to make the state diagram. Okay, so to understand these things, what we need input information, we need output information, we need state information, and based on that, let us come up with some conclusion, or let us come up with some conditions. Condition number one is the state a will change from a to b if x is equal to 1, and that will produce output y. A second condition is it will not change its state if the state is a, and it will be again at state a if x is equal to 1, but that will produce output y. Okay, so if I have these two kind of conditions, so let us try to see how we can draw the state diagram considering the Mealy and the Murray model. Okay, so let us consider one by one. If I'm considering the Mealy model, how it can be represented. Okay, let us try to see. As we know that a and b are two different states here. If a and b are two different states, so here I can have one state which is a, and the second state I can have that is the b. Okay, so a and b, these two are the two states. Now, how to represent in the Mealy model? In the Mealy model, what are the conditions? A will change from a to b if, yeah, let me change the color so that will help you to understand. So it will change from a to b if input is x, means input is 1, and that will produce output y. So x slash y is the condition for this one. Initially state was a, I am moving to state b if x is equal to 1 and the output what it is producing is y. So x slash y, this will be the representation for the first case. Now let us talk about what is the representation for second case. Initially input is a, and state is a, and the state is not going to change. It is going to be same. Okay, so there is no change in the state. It was a, and it is going to be a only, and the condition for input is x is equal to 0, so we can call them x complement, and that is producing output y, so slash y. So this is the representation of Mealy model. Okay, so based on the conditions whatever given, we can simply represent the Mealy model. Okay, so if you have any doubt at this point, you can ask the question how I draw this Mealy model. Okay, let me complete the Murray model as well, and then try to differentiate it. Okay, suppose considering the same kind of conditions, Okay, if I want to make the model for the Murray, then how we can model it? Okay, so to model this one, I have a two states. Okay, just like the previous one, I can have a two state. One state is A. Okay, one is the A, and the second state is B. Okay, so these two are the state. Now, what the conditions are saying? Let us try to see. Condition first is saying the state will change from A to B if x is equal to 1. Okay, so that will change from A to B if x is equal to 1. So I will use normal one, not the complemented one. So x is equal to 1 means I have to use normal x. If x is equal to 0 means I have to use x complement. This is the meaning of this thing. Okay, so if x is equal to 1, then it will change from A to B, and that will produce output y. So output y will be given over here. If initially input is A, and state is A, and the input is x, then it will switch to state B, and that will give you the output y. So this is the state. Now let us consider the second case. If I'm considering the second case, in the second case, if x is equal to 0, okay, then it will produce y, but it will be in the same state, means A to A. It will be from A to A only, and the condition is x complement, and that is producing output y. Okay, so this is how the state diagram for the Murray model will look like. Okay, so this is the difference of representation of Millet model and the Murray model. If you have any doubt at this point, you can ask the questions. Anyone?
Excuse me, sir.
Yeah, please.
Sir, have you written y bar?
Where?
Sir, in the Murray model?
No, it is not bar. I'm just differentiating it. Yeah, so it is just to differentiate state in the output. Okay, it is not a bar. It is a differentiation between these two. Okay, the upper part of this bar is this line is the state, and the lower part of this line is the output. This is not the complement. You got the answer?
Yes, sir.
Okay. So these are very important actually. So whatever the input variable I have, whatever the output variable I have, whatever the states we have given, and what are the conditions to switch to from one state to another one, based on that we can come up with the model, Murray model and the Millet model, and these are the models how it will look like. Okay, so see, these are the different representation. That's it. If we talk about the Millet model, we have to give input and output outside during the transition, at the transition time. But in the Murray model, I have to give only input in the transition, and output will be given at the state. Okay, because that is going to become what is the state value. So this indicates what is the state value. So this is the representation of Murray and the Millet model. One thing that you have to remember in the Murray and the Millet model is, like, suppose if we are talking about the Murray model, in that case, the output combinational circuit should that should not depend on the input one. And in the Millet model, the input will also be responsible to generate the output, or simply the output combinations or logic circuit is also the function of the actual input. So this is the only difference that you have to consider. Okay, so the next and important, the last parameter that I have to consider is the transition table. What is this transition table? Transition table is like, see, state diagram and the state table represents the states using symbols or the names. Okay, transition table is a table, is a kind of state table where states are represented by actual binary value. So if the states are represented by, so here if you see, A and B are some symbols which we are using to represent in the state table, state diagram. But if I'm talking about the transition table, here in the transition table, we will not be represented in terms of A and B, X, Y, Z. Will be represented in terms of 0 and 1. Okay, so if it is X, then I will use 1. If it is X bar, I will use 0. Okay. So if they are represented in 0 and 1, then we can call them the state table. So these are some of the representation in the Murray and the Millet model, and that you should understand what is the difference between all these things. Oh, sorry. So you should know these things. So if you have any doubt, then you can ask the question. Otherwise, we need to move ahead. Fine. So the basic comparison between Murray and the Millet model, yeah, this is the basic comparison that we should know. So the Millet model, if we talk about Millet machine change its output based on the current input and the present input, and the output of Murray model only depends on the current state, not the current input. Okay, so these are some differences which I have already told you before, and that has been table, like I have just made prepare a table, and you can go through it. It's not that much important, but yes, if you want to know the difference between these two things, you can go ahead with these things. Okay, so if you see here, the Murray model are easy to design, but the Millet model is not necessary they are easy to design. So the complexity of the Murray model is less as compared to the Millet model. We will come up with some example, then you will get to know that how it is working. Okay, so if you talk about the counters are the example of Murray model. Okay, but the counter cannot be considered in the Millet model. Okay, so these are some differences that you can go through it, you can read it, and this is how it can